Hello and welcome back. So, in today's lecture we are first starting with the concept of speed, like there are different mean or average speed inside a gas assembly, and we will be first discussing those. Okay. So, let us focus on this. There are, as I have said, there are several different we can define at least 3 different speeds in a average speed in a gas assembly. The first one is the mean speed. What do you mean by mean speed? Mean speed is simply if there are n1 number of particles moving with C1 speed, average speed of C1 or speed of C1, absolute speed of C1, n2 number of particles moving with absolute speed of C2, so on and so forth, and n small n number of particles moving with speed Cn, then the mean speed of the gas assembly is defined as n1 C1 plus n2 C2. So, basically this sum. Now, this sum can be brought down in form of an integration, which is 0 to infinity C dnc, where dnc is the distribution from or rather the expression of dnc is I am not going to write at this here as of now, but as you know, this is from Maxwell, or rather I would write from Maxwell's distribution. Right. So, once we try to compute this integral, it will be 4 pi n a cubed. At present I am just writing in terms of a and b, we are not writing the full expression for a and b, and then this integration becomes 4 pi n a cubed in the numerator and capital N in the denominator, with whole multiplied by this integral 0 to infinity c cubed e to the power minus b c square dc. Now, this integration can once again be brought into the form of a standard integral in terms of the gamma function, and this is nothing but 1 by 2 b square gamma 2, which is gamma 2 is equal to 1. So, we have 1 by 2 b square. So, once we substitute for this one, we have c bar, which is the mean speed, is equal to 2 pi a cubed by b square. Now, this is the time when we can actually put the values of a and b, and once we do that, we put the value of a as m by 2 pi kt whole cubed whole to the power 3 by 2, and b as m by 2 kt whole cubed. Sorry, it is b square and a cubed. So, it will be right, b will be m by 2 pi kt whole square, not whole cubed. Sorry, there is a small mistake here. Yeah, root m by, yeah, it will be simply m by 2 pi kt, and finally we have c bar is equal to root over 8 kBt by pi m, which once again if we evaluate the factor 8 by pi is nothing but 2.55 kBt by m. Right. Next we define the root mean square or R.M.S. speed, which is once again is a mean speed, and so first we define the mean square speed, which is c square average, and then we define the root mean square speed as capital C, which is equal to root over of mean square speed, which is c square average. Now, all we have to do is we have to find out the expression for c square average, which is n1 c1 square plus n2 c2 square all the way to capital N subscript small n cn square divided by n1 plus n2 plus n3 all the way to nn. Now, this once again the denominator is nothing but the total number of particles, that is capital N, and the numerator is integration of c square dnc, right. So, the integration as numerator is c squared dnc, integration 0 to infinity, and the denominator is this one. So, once again we compute this integral in terms of a and b at present. So, we write 4 pi a cubed, and this integration becomes e to the power 4 e to the power minus b c squared dc, and right. So, here you see the power of c has increased. So, the gamma function it will be 1 by 2 b to the power 5 by 2 gamma 5 by 2. Now, gamma 5 by 2 is nothing but 3 halves times half times gamma half, and gamma half is nothing but root pi, right. So, once we put this in, we have 12 pi whole to the power 3 half a cubed by 8 p whole to the power 5 half. Simplified in terms of a and b, it gives you the expression of c square, which is equal to, or c square average, which is equal to 3 kBt by m, and then the root mean square value is capital C is equal to root 3 kBt by m. Also, it is convenient to write this as small c with a subscript of R.M.S. Okay. So, we can either write capital C or we can write C R.M.S. and the expression is root over 3 kBt by m. Now, there is another possible mean speed that we can define, that is the most probable speed. What do you mean by most probable speed? Most probable speed means if we draw the Maxwell-Boltzmann velocity distribution function, you see it looks like it has a it goes up, then reaches a maxima and then comes down. Now, the speed that corresponds to this maximum point is called the most probable speed. Now, in order to get that, what we have to do is we have to take the function f c, capital F c, that is the Maxwell velocity speed distribution function, and we have to take the derivative of that function with respect to c, and then we have to set this equal to 0. Now, once again we, just to avoid complication, we are not writing a and b explicitly, we are just writing the expression for a and b at present. We are simply differentiating the expression 4 pi a cubed c square e to the power minus b c square, and this derivative you see once we set this equal to 0, many terms cancels from the left side, from the left hand side and the right hand side, because it will be this one equal to this one when we put dfdc is equal to 0. You see 8 pi a cubed and 8 pi a cubed cancels out, yeah, and 1 c cancels out with this c square leaving behind c cube leaving behind c square, and finally after some simplification you have to of course put the value of b here, because you get Cm is equal to 1 by b, and this is nothing but root over 2 kBt by m, right. So, okay, now I think we just have to make a small correction, b square will be m by 2 kt, yes, perfect, m, so it was right. So, b is this, so b square will be m by 2 kBt, perfect. So, we get all three expressions. One is for the most probable speed, which is root over 2 kBt by m, then we have the R.M.S. speed, which is root over 3 kBt by m, and finally at first we have derived the average speed, which is, or the mean speed, which is root 8 by pi kBt by m, or 2.55 kBt by m whole root. Now, in terms of the speed distribution function, where does this 3 speed where does it fall in the distribution curve? Now, of course, we see very easily that this one is the lowest. It comes with a prefactor of 2 with kBt by m whole root. This one is the highest because this comes with a prefactor of 3, factor of 3, and this is something in between these two speeds, which comes with a factor of 2.55. So, once we plot that, it is just a quantitative plot. It is not exactly, I am not using exact numbers here, but if I draw the distribution function like this, the lowest one will be the most probable speed, which corresponds to this point, the topmost point of the distribution function, and this we denote with Cm, then we have the mean speed which is C bar, and then we have the RMS speed which is either capital C or C RMS, and we see C RMS is greater than C bar, which is again greater than Cm, right. And of course, we can compute the ratio of these three speeds, and you see that of course, Cm is the smallest, and we have this relation that Cm is to C bar is to C RMS is 1 is to 1.128 is to 1.1224. Okay. So, it is obvious that they are very close to each other. Of course, there is a small difference. We will look into the numbers now, because but we will do some problems, but before that let me quickly tell you that there is a possibility of derive a pressure expression from kinetic theory. Now, this pressure expression is kind of approximate, that is why I am not doing it now. What I will do is I will just wait till we go into the section of mean free path and collision, because that picture gives you something more realistic view of the situation. Because we all know that that is one of the fundamental assumption of kinetic theory, that the gas particles they collide randomly, of course, they changes direction. Those things will not be was not considered in the elementary treatment of pressure while deriving from kinetic theory. But little more advancement from the elementary kinetic theory is when we introduce collision. But surprisingly, for both the treatments, from the elementary kinetic theory and from the concept of mean free path, we get the exact same expression for the pressure, which is P is equal to P is equal to 1/3 m n by V C RMS square, right. This n is the total number of gas particle which is present, V is the total volume of the container. So, n by V sometimes written with a small n, which is the density or per unit volume. I have just avoided this because that small n is very confusing. Sometimes we we mix it up with the number of moles that is present. So, once we will we have to write this density explicitly, probably we will try to use some slightly different symbol for it, but for now I have just written n by V. Okay. So, with this what we are going to do is we are going to do some problems. I have a problem set prepared for you. It is not complete yet. I have at present I simply have added 4 problems, right. Just a minute, it is a bit slow. Anyway, so we can go into the problems. The first 2 are really elementary in nature. We have to convert a specific amount of 25 grams of water to moles of water, and we have to convert 2.5 moles of KClO3 to grams. Grams are actually kgs, because kg is something that we will be using explicitly. I have just taken this example, but gram to kg conversion we all know. And then there are 2 very basic problems from the kinetic theory of gases, whatever we have discussed so far. Okay. So, let us go back here, right. So, for problem 1, it is super simple. We have the molecular weight, we know that the molecular weight of water is 18 approximately. The exact expression for molecular weight, if we have to. So, basically for both these problems we have to compute the molecular weight. So, what we have to do is we have to add up this atomic weight data from the periodic table. So, for exact numbers or exact value of this mole or weight, we have to go to 3rd, 4th or sometimes 5th decimal place accuracy, but here only the approximate calculation, and for most part of our discussion we can use the approximate number. For example, 18 for water is something very, that gives results within the error of limits of our calculation and computational error. So, we will just take 18 as the molecular weight of water. That means 18 grams of water makes 1 gram mole. Okay. So, there is a I probably should have written 1 gram mole instead of 1 mole, because ideally 1 mole is expressed in kgs. So, 18 kgs of water will be 1 mole. Probably I should make this small correction here. Yeah. So, this is 1 gram mole, oh, sorry, wrong color. Yeah, 1 gram mole, right. So, this is once again gram mole, and this will also be gram mole only, right. Right. Yeah, so there is also a problem here. This should be ideally 1 mole of KClO3 should be expressed in kgs. So, yeah, so this is actually, I will just convert this to 1 gram mole once again. Do not worry, I will make the necessary changes in the problem set also, but I think the idea is clear that we have 1 gram mole of KClO3, which corresponds to 122.55 grams for problem 2, and then 2.5, sorry, it should be not moles but gram moles once again. Yeah, this will be 306.37 grams, which is 0.30637 kg. Okay. So, of course, if we want to compute the number of moles, we have to express everything into kgs, but the basic calculation does not change. Okay. So, now let us look at problem 3, which is calculate the pressure exerted by an ideal gas having 2.5 into 10 to the power 19 molecules per cc at 27 degrees centigrades. Right. So, what is given is the number of molecules per cc. Once again, please note that we are dealing with number of molecules per cc and the temperature is given in centigrades. Now, how to compute this, compute the pressure? Please remember the ideal gas expression is PV is equal to N kBT, right. PV is equal to N kBT. Now, 2.5 into 10 to the power 19 molecules per cc is actually, sorry, it should be once again there is a small mistake, it should be 25, because the factor between cc and meter cube. So, it will be 2.5 into 10 to the power 25 per meter cube. The factor between cc to meter cube is 6, so 10 to the power 6. So, we have to just multiply this number with 10 to the power 6 in order to get the number of molecules per meter cubed, right. Now, then from here we can just rewrite this as P is equal to N by V kBT, and N is nothing but the number of molecules per unit given volume, right. Now, here again we have to consider SI units. So, we are converting the temperature to Kelvin. 27 degrees is equal to, this is nothing but 27 degrees, right, and the Boltzmann constant Kb is also given as 1.38 into 10 to the power minus 323. What is the unit of this? This is joules per Kelvin, right. So, this is also in an SI unit. We have to always keep this in mind. Unit is very important, which was not okay. In this problem there was a problem with the mole and gram mole, but I will correct it in the final version of the classroom problem set. Here there is no such confusion, and once we compute we get, and the unit of this pressure after we substitute P, the values of N by V as 2.5 into 10 to the power 25, Boltzmann constant, and the temperature is 10.38 into 10 to the power 4 pascals. Of course, the unit is Newton per meter cubed, which is nothing but pascals, right. Okay. So, for the fourth problem, it is once again a very easy problem. We just have to calculate the most probable speed, average speed and root mean square speed of oxygen molecules from the following data. M, the mass of one oxygen atom is given. Once again you see this mass oxygen molecule is given in kgs here, and then we have the Boltzmann constant, which is 1.38 into 10 to the power 23. I forgot to include the units, but the units will be joules per Kelvin. Okay. Now, what we have to do in order to calculate all these three velocity or three speeds is we have to compute the quantity kBT by m, right, this quantity. And once we put the numbers in and we get we get a number for this kBT by m. Now, what is Cm? This is simply root 2 kb. So, I should write kb actually here, kBT by m, this is kBT by m and kBT by m. So, Cm is root 2 kT by m, C bar is equal to 2.55 kT by m and C R.M.S is equal to 3 kT by m, and the numbers are this. So, you see they are close, like, but not very close, they are significantly different for oxygen molecules even at room temperature. 27 degrees is essentially the room temperature. So, you see the spread is from 395 meters per second, so almost 400 meters per second to almost 485 meters per second. So, this is a considerably wide spread. Of course, it depends on what molecule you are dealing with, what temperature you are dealing with, but this spread is significant for most of the practical purpose. Okay, so we will stop here today, and in the next class we will be talking about degrees of freedom of a gas molecule.